3.3, vectors in the plane. So a vector is a directed line segment with initial point P and terminal point Q. Examples of vectors are force, velocity, and in force and velocity, we need to know both magnitude and direction. So not a single number, but both magnitude and directions characterize a vector. So two-directional line segment with the same magnitude and direction are co-equivalent. So equivalent vectors have the same magnitude and direction. So the magnitude of our vector PQ, magnitude of PQ is also the length, and we indicate that with double lines, the magnitude. Example, show that PQ and RS, these two vectors are equivalent. If P has coordinates 0, 0, Q has coordinates 3, 2, R 1, 2, and S 4, 4. We can draw a picture. Sketch those vectors. So P, the initial point, is the same as the origin, and Q is 3, 2. So this is Q, is a vector PQ, and R has coordinates 3, 2. Let's see, R has coordinates 1, 2. So that's here, this is R, and S is 4, 4. So here. All right, so to show that they're equivalent, we need to show they have the same magnitude and the same direction. Let's start with the magnitude. What is the magnitude of PQ? Well, that is a hypotenuse in that right triangle here. That's a right triangle. So PQ, the hypotenuse is square root of 3 squared plus 2 squared, because this distance here is 3 and this distance here is 2. So that is square root of 13. We're just going to leave it like this. And the same way, the magnitude of vector RS, we can still draw a right triangle here. And we see this side here is 2, and this side is from 1 to 4, that is 3 as well. So square root of 3 squared plus 2 squared, which is again 13. The two vectors have the same magnitude. Now we have to find the direction. So we're going to use a slope. What is the slope of PQ? Rise over run. So it is up 2 over 3. And it's the same as the slope of RS, up 2 and over 3. So these two vectors are equivalent. Now we're going to talk about component form of a vector. component form of a vector. First, let's clarify what a standard position is. Standard position of a vector is where the initial point coincides with the origin. So let's draw a picture. I can draw a vector v anywhere, okay? So these are all equivalent vectors as long as they have the same direction and the same magnitude. But what is really helpful is if I can draw the vector v with the initial point at the origin. So we say this vector v is in the standard position. So the coordinates of a terminal point here is, let's say they're v1, v2, then we say the component form of our vector is also v1, v2. So if the vector is in the standard position, then the coordinates of the terminal point are the same as the components of the vector. So I can label this point Q and say the coordinates of the point Q are v1, v2. You notice I'm using parentheses for the coordinates of the point, but those symbols for the components of the vector to distinguish. Okay, so component form of a vector is really easy to find if the vector is in the standard position, but if it's not, we can still find it. Component form of a vector with initial point P with coordinates P1, P2, and terminal point Q with coordinates Q1, Q2 is, and we have a formula, a vector PQ has components Q1 minus P1, Q2 minus P2, and they're the same as V1, V2 as before. So we subtract the coordinates of the point starting with the terminal point. So terminal point coordinate minus initial point coordinate. Okay, so if the vector v has a magnitude 1, we call this vector unit vector. So a vector with a magnitude 1 is called a unit vector. A vector v with a magnitude 0 is the zero vector. Okay, we distinguish the zero vector from the number 0 by putting a symbol for a vector on top of the 0. Okay, so if I have two vectors, u with components u1, u2, and another vector v with components v1, v2, we say the equivalent u is equal to v if and only if the corresponding components are equal. So u1 is equal to v, u1 is equal to v1 and u2 is equal to v2. So example, find the component form and magnitude of the vector v find the component form and magnitude of the vector v with initial point for -7 and terminal point negative 1, 5. We can draw a picture or we can just calculate. So P, our initial point, is 4, negative 7, and Q, our terminal point, is negative 1, 5. So to find the component form of our vector V, we need to find V1, the first component. So V1, as you look in the formula before, is Q1 minus P1. So that is negative 1 minus 4, or negative 5. And V2, the second component, is right here, Q2 minus P2, so the second component, or 5, minus negative 7, which is 12. So our vector V have components negative 5, 12. So we found the components of the vector. Now we have to find the magnitude. So the magnitude of our vector V is just like we did before. We do square root of the components squared. So that is 169, which is a perfect square, 13. So let me make a note about the magnitude of a vector here if it's not clear. So a vector V has components V1, V2. The magnitude of the vector V is the length. So we find this by square root of V1 squared plus V2 squared, just like we did before with the hypotenuse of the right triangle right here in example 1. Okay, vector operations. Vector operations. We're going to talk about scalar multiplication. That is multiplication by a scalar or by a number, or multiply a vector by a number, and also vector addition. A definition. Addition of vectors. So if I have two vectors u1 with components u1, u2, and vector v with components v1, v2, these are vectors. The sum u plus v is also a vector, and we're going to add the corresponding components, u1 plus v1, u2 plus v2. So we call this sum. It's a vector. And the other operation, we'll give a definition for scalar multiplication. So k is a scalar or a number. That's what scalar means, a number, real number. Then k times the vector u is equal to k times the component form of our vector u1, u2. So that is k u1, k u2. So we simply multiply by k each component of the vector. So for example, if I have a vector u right here, then the vector 2u will have the same direction, but twice as big. So that's what it means to multiply by a number. If the number is positive, we keep the same direction and it changes the length of the vector. And if the number is negative, what is the meaning of the vector negative v, for example? So that is the same as number negative 1 times the vector v, which is negative 1 times the components v1, v2, which is negative v1, negative v2. So if this is our vector v, then negative v is the same magnitude, has the same magnitude, but opposite direction. Okay, now subtraction of vectors, I didn't mention it, but subtraction is the same operation as addition. So what we understand by u minus v, it is u plus negative v. So we already discussed the meaning of vector negative v, so we just have to add u plus negative v. Geometrically, we can show a picture. Okay, so if I have a vector u somewhere here and a vector v over here, let's first show what is the vector u plus v, or where is it? So here's u, and so we're gonna translate v, so it starts where u ends. So I'm gonna draw a equivalent vector, a vector v. So that initial point of v, it's where the terminal point of u ends. So this is u plus v. I'm gonna show in blue, this is u plus v. Okay. So now we can show what is u minus v. If I have a vector u over here and another vector v over here, we want to show geometrically where is the vector u minus v. So negative v is the same vector v, but with opposite direction. So I can sketch it over here. This is negative v. And now I have u plus negative v. So here's my resulting vector u minus v is the blue vector. Okay, so this is the geometric, the geometry behind vectors. So another example, if I have a vector v with components negative 2, 5, and a vector w with components 3, 4, find A, the vector 2v, B, find the vector w minus v, and C, v plus 2w. You could draw them, but you don't have to. To find the vector means to find the component form. So part A, 2v, we simply multiply the number 2 by the components of v, negative 2, 5, and that is negative 4, 10. So this is our new vector. Part B, we need to find w minus v. How do we subtract vectors in component form? We subtract the corresponding components. So w is 3, 4, and v is negative 2, 5. So you subtract the corresponding components, so it'll be 3 minus negative 2, 3 plus 2, and 4 minus 5. So that is 5, negative 1. And finally, part C, we need to find v plus 2w, write each vector in component form. So v is negative 2, 5, plus 2 times 3, 4. And when you simplify, you should get 413 for the resulting vector. Now, properties of vectors. Properties. Let u, v, and w are vectors, and c and d scalars or real numbers. Then we're going to write some properties here. Number 1, u plus v is the same as v plus u. So the order is not important when we add vectors. Now, if we have three vectors, u plus v plus w, how do we add them? It doesn't matter. We can add the first two and then the third, or we can add the second and the third to the first one. Number 3, u plus the 0 vector is the same as u. So the 0 vector doesn't change anything. Number 4, if I add u to the opposite vector of u, then we get not just the number 0, but the vector 0. So when we add or subtract vectors, we get vectors. Now c times d times u, so we have two numbers, we can multiply them first and then multiply by u. Number 6, c plus d times the vector u, you can distribute here and do c times u plus d times u. Number 7, c times u plus v, we can distribute c times u plus c times v. Number 8, number 1 times the vector u is vector u itself. 0, however, times the vector u is equal to the 0 vector. And lastly, number 9, the magnitude of c times vector v is equal to the absolute value of the number c times the magnitude of vector v. So these are the properties we use when we manipulate vectors and their operations. Now, very important to mention what's a unit vector and how to find it. Unit vector. We already know a unit vector is a vector with magnitude of 1 in any direction, so there are infinitely many unit vectors. But what we want is to find the unit vector in the direction of a given vector v. So if I have a vector v somewhere here, we want to find a unit vector in the same direction. Okay, so what we do to find this unit vector, we divide our given vector v by its magnitude. And there's another way we can write it down. We can separate this 1 over magnitude of v, which is a number, and multiply it by vector v. So it's a scalar multiplication, number times a vector. So note that the unit vector u has a magnitude of 1, and it's in the same direction as the given vector v. So let's have an example to see how that works. Find a unit vector in the direction of v and v is given with components -2, 5. So find the unit vector in a direction of v with components -2, 5 and verify that the result has a magnitude of 1. Okay, so we have given vector v with components -2, 5. To find the unit vector, we are using a formula. So u is equal to the vector v divided by the magnitude of v. So our vector v is -2, 5, and we're dividing by the magnitude. We know how to find the magnitude, negative 2 squared plus 5 squared. So that's negative 2, 5 divided by square root of 4 plus 25, 29. Okay, so let me write this down, separate the number with the vector, and now multiply the number 1 over square root of 29 with the component. So negative 2 over square root of 29 and 5 over square root of 29. So this is our unit vector. But now we have to verify if indeed the magnitude of this vector is indeed 1. So how are we going to do this? We're just going to calculate. So check if the magnitude of our vector is indeed 1. Well, that will be square root of negative 2 over square root of 29 squared plus 5 over square root of 29 squared. And that is square root of 4 over 29 plus 25 over 29, which is square root of 29 over 29, which indeed is 1. All right, another example. Writing a linear combination of unit vectors. So let U has initial point 2, negative 5, and terminal point negative 1, 3. Write U as a linear combination of I and J. So I and J are special unit vectors. They're special because they're along the x and the y-axis. So here's I and here's J. So we know there are infinitely many unit vectors in all directions, but the unit vector along the direction of positive x-axis, we call it I, and the unit vector in the positive y direction, we call it J. So I and J are standard unit vectors. Okay, so back to our example to write our given vector 2, negative 5 with initial 2, negative 5 and terminal negative 1, 3 as a linear combination. First, you have to find the component form of U. Find the component form of U. So we have a formula for that already. So that is, we subtract the second coordinate minus the corresponding coordinates, the second point minus the first, so negative 1 minus 2, and then 3 minus negative 5 become 3 plus 5. So the components are negative 3 and 8. So our vector U has components negative 3 and 8, and another way we can write this down is negative 3I plus 8J. I'm going to show you this in detail, how we do this. So let's start with U being negative 3 and 8. And I can write this down as negative 3, pull it out, and here inside 1, 0, plus 8, pull it out, 0, 1. So if you check this backwards, multiply negative 3 times the components, 8 times the components, add them up, you'll get negative 3, 8. But now 1, 0 is our unit vector I, right? These are the components of a unit vector I, 1, 0, and J has components 0, 1. So we have negative 3I plus 8J. So that's how we write a vector as a linear combination of I and J. And we can write this for absolutely any vector we can write it in this form. So another example, if I have a vector with components 3, -7, how do I write in terms of I and j? 3i minus 7j. So here you go.